Hello, this is a list of new nodes which we are going to discover along this lesson. This time the list of new nodes is small, but the lesson is very informative. Whole lesson is about matrices, which give us enormous potential to manipulate geometry. Excellent, let's get started. Create a torus. Jump into it. Put a 50 for rows and 100 for columns. Now let's remesh this geometry just to get triangles. Put a 0.16 for target size. We can also increase the amount of iterations. Now let's create a facet node. Connect to it the geometry. Let's toggle the unique points checkbox just to detach all triangles from each other. To make sure that they are all separated, we can simply use an exploded view. That's it, all triangles are separated. Now I want to extrude the triangles just to give them a little thickness. Let's also toggle this checkbox just to have back faces. Okay, now let's connect the extruded geometry to the exploded view and see how it looks. That's it, they all have a little thickness. We can already delete this node, we no longer need it. Now let's drop down the attribute VOP. Connect to it the geometry, then dive inside. Okay, before I start working with matrices, I want to quickly colorize this geometry. For that I'm going to use relative bounding box information. Let's give it all the necessary inputs. Then, connect the output vector directly to CD. Here we go, we get a nice color gradient along 3 axes. To saturate the colors, we can use the power node. Let's increase the exponent parameter. That's it, we got more saturated colors. Okay, now we can start working with matrices. First, let's create a translate node. This operator translates a 4x4 matrix by amount vector along the XYZ axis. In order to translate this geometry, we have to multiply the position vector by the matrix. Take a look, now we can translate the geometry along any axis. Since we won't touch color anymore, I suggest drag away these nodes to make room for further workflow. We can duplicate the geometry VOP output. Hold Y key and drag over this wire just to break the connection. This one also. Look, now we have 2 geometry VOP output nodes. On the first one, the position vector is connected, on the second one, the color vector is connected. Well, let's arrange the nodes and move on. Now I want to introduce you to a rotate node. This operator applies a rotation by radians to the given 3x3 or 4x4 matrix. Axis specifies the axis of rotation, which can be an arbitrary direction and must be normalized. Now let's multiply the position vector by the rotation matrix. Look, now we can rotate our geometry around any axis. In fact, it does the same thing as a rotate by quaternion node. Now I want to introduce you to the scale node. This operator scales a 3x3 or 4x4 matrix by amount vector along the XYZ axis. Now let's connect the output matrix to the multiply node. As you can see, we can scale up and down our geometry. Of course we can scale along an individual axis. Look, with these 3 nodes, we can move, rotate and scale as we like. Now I want to show you how important the order of these 3 operations is. Let's move the torus away from the origin, then try to rotate it. As you can see, the rotation occurs around the origin. Let's check the scale as well. Look, the scale also occurs relative to the origin. Now let's delete these connections, then start ordering in a different way. The first will be scaling, rotation will be the second, and the third is already translating. Now let's check what we have. The scale works correctly considering the orientation in space. The rotation occurs correctly around the center of geometry. The translation also works as it should. Okay, let's return the default values for all of them. Now I want to manipulate each extruded triangle separately. Let's jump at the object level. I'm going to do the same trick which we did with quaternions, extract the centroids for each piece. For that we need a unique attribute for each piece that can be generated by the connectivity node. The unique attribute is a class. Now let's create an extract centroid node. Select a point, then specify a class attribute. Here they are, the centroid of each. Connect them into the second input, then dive inside. Let's organize the workspace a bit to make room for further workflow. Select all nodes associated with colors, then create a network box. Call it Color Setup. Then minimize the network box. We hide the nodes because we are not going to touch them. Now let's drop down the import point attribute node just to bring in the centroid positions. Connect to it the second geometry. We have to specify the point number. In this case, a unique attribute called class must be used as point numbers. Let's create a bind node and bring in the class attribute. The type is an integer. Connect it to point number. Okay, we import the centroid positions. Now I'm going to subtract the centroid positions from point positions just to move each piece to the origin. Excellent, they are all in the origin. We are going to return them to their original position after matrix multiplication. Hold Alt and click just to add a dot and change the wire shape. Here we go, we have returned the original position of each piece. Let's tweak the scale matrix properties and see what we get. As you see, all pieces are scaled relative to their centroids. Now let's tweak the rotate matrix. Look, the rotation also occurs around its centroids. Excellent, now I want to scale each piece randomly. For that, let's create a random node. Plug a class attribute to it. Now we have random float values for each piece. Since the scale amount is a vector, we can turn each random value into a uniform vector. To do that, we just need a float to vector node. Connect random output to 3 components just to make a uniform vector. The output vector to amount. That's it, we scale each piece randomly, and they all have a uniform scale. Now I suggest using some noise instead of a random node and see what it looks like. Let's create a turbulent noise. Plug the centroid positions to it. We need one more float to vector node, let's create it. Connect the noise output to these 3 components. The output vector to amount. Let's also adjust the noise amplitude. Here we go, now we scale them based on the noise. Looks nice, let's go ahead. Now let's disconnect the scale vector and start to manipulate the rotate matrix. For rotation, I'm going to use the bounding box information. As you remember, in this setup we have already imported the bounding box information. We're gonna use it again. Let's create a getVector component node. Plug the bounding box vector to it, then extract the X component. Now we're going to use this information to manipulate the rotation matrix. Plug it to the rotation angle. Here we go, the rotation gradually increases in the direction of the X-axis. To control the magnitude of the angle, we can simply add multiplier. Okay, now let's rotate them along the Y-axis. I think in this case it is better to delete the multiplier. Look, there is no rotation at the bottom of the torus. At the top we have a maximum rotation. That's it, let's move on. Now I'm going to manipulate the translate matrix. Let's create a turbulent noise. Plug to it the centroid positions. Select the original Perlin noise. The output must be 3D noise. Let's get the turbulent noise closer to the translate matrix. Then plug the noise to the translate amount. Now let's adjust the noise settings. Excellent, we are able to translate each piece locally. Let's also add the rotation we just created. The only thing is to change direction along the X. And finally, let's add a scale. Here we go, this is a combined result of manipulation of all three matrices. Sure, it looks weird right now, but you can do cool things using these techniques if you want. Okay, we can continue. Now disconnect all manipulations to return the torus to its original state. This time I want to show you how you can rotate each piece around an arbitrary vector. As an option I will use torus normals. For that let's jump at the object level, then create normals.